So today, maybe I'm just telling you who I am for those guys that don't know who I am. I'm Anton Janovsky. I've got a small electronic company in South Africa. We manufacture some microcontrollers and antennas and radios and so on. Also, I'm software architect for Standard Bank South Africa, and I'm looking at African regions of banks for South Africa. So today I'm going to try and give you some feedback of how far we are with the AfriCUBE satellite. And specifically in the beginning, I'm going to give you the details around where we are with the power supply, because that's actually the last board that we need to build. And then after that, I will just go on the general details of what's still outstanding and what we've done. Let's take it from there. So just to give you a quick view of where we are. So we've got the space frame, and in the space frame we can fit these boards. We've got the STR receiver board, STR transmitter board, onboard computer, battery and orientation. So that is the battery sits in the middle, and we need gravity or the heaviest components in the middle of the satellite, so it's not reasonably balanced, so that if it does rotate in space, that it doesn't swing around in different angles, but hopefully rotate around the middle. Then we're going to have the power supply board, which I'll take you through today in details. That's our version 2 board. Then we've got the undefined board, which is a spare board. And then we've got a separation and experimenter board, and I'll give you guys some details about that. That's probably where we need input from universities or schools, what we want to put on there. And then the last one is just the bottom plate. And then it's got 4 doors that open up, basically. Why is this thing not reacting? Sorry, I'm trying to get to the next. There it is. Okay, so basically we've looked at different cells, and we've identified this product, which is off-the-shelf product, which delivers or has a very good efficiency relationship to its size. And yes, all the specifications around it. I'm not going to go through too much detail, but I think the criteria that's important here is this 28% efficiency, which is pretty good for what we want to use it for. We also looked at another cell, very similar efficiency, but the costing at this stage were much more than the other one we've selected. So this was the original test that we've done with one assembled side panel. We're going to have 13 of these panels on our satellite. The reason why we have so many panels is really from a one cube satellite point of view, to really have a high power transponder on it. Our limitation is really power. So if we can have enough power, we would be able to run a transponder for long periods. By calculating the total power that we could get out of the solar panels, this is sort of the amount of power we were looking at, about 2.956 watts that we possibly going to get out of the solar panels. So this was just some calculations we've done to see what is the effect of different angles of sun rays hitting the surface of the solar panel. And by looking at the 0 to 90 degree and 270 to 360 and so on, the different angles, what kind of power we can expect basically from the panels. So we also have to look at worst case scenario and best case scenario scenarios of power generation on the satellite. So we try to get the obvious full power capability directions, and then the worst case scenarios. I think the worst case scenario is probably this one here, if I'm correct. And so this scenario, so that then we calculated the average power, because we've got that calculation that I've showed you in the previous presentation. We can calculate what would be our average power for the satellite. So here's your worst and best case scenarios. So on average, we're looking from about a 2.2 watt to a 2.884 watt capability, right? And that is if we have the full power capabilities of lower angles. So what I mean by that is if we've got a very skew angle hitting the panels, and for instance, these ones, let me get my mouse, these 2 and 1 will be 45 degrees, but if it rotates a little bit more, then you might get different angles. And the problem is, if you have different solar panels with different power generation capabilities, how do you, how can I say, harvest the low angles and the direct angles power, and then harvest all that power and get it into a battery or be able to use it? The big problem is that most regulators, if you would look at them from that point of view, you can't just use diodes and combine all the solar panels together, because the only power you're going to get is the solar panel that's obviously directly in the sun at 90 degrees. So we had to think out of the box here, to think of a way to be able to harvest low power solar angles and high power solar angles, and then combine the power, and then take that total power and run the satellite, and as well charge the batteries, right? So that's the essence of the problem. So looking at all those problems, we have to look at a capability that will give us the power that we need, so we can harvest all those different anomalies, right? And then there's, never mind those anomalies, we've got rotation, especially when the satellites get launched, they get pushed out of the P-pods. It's like a long square, how can I say, long square tubes, and they basically put 3 1 CubeSats in that tube, and it's got a small spring at the end. And when the door opens, these satellites gets pushed out. And one of the requirements we have to have is we have to have small little springs on 2 of the legs of the satellite, so that even between the satellites, we can push ourselves away from the satellite next to us. If all those things happen and gets pushed out, there could still be the possibility that the satellite that we're pushing ourselves away was already rotating, and so on and so on. So it could influence the way we actually move into space, right? That original. Now, normally what happens is the satellite will rotate, but the satellite, normally, if you've got a permanent magnet stabilization board on board the satellite, the permanent magnets will use Earth's gravitational force and will eventually stabilize the satellite in a certain rotation, depending on how the magnets are placed on that board. And it will rotate the antennas to Earth, and hopefully that rotation will then be the stabilized rotation. Now, normally that stabilization, that especially in the beginning, if you look at majority of satellites, it normally takes about 7 weeks. So for the first 7 weeks, we could get a lot of Doppler effects as antennas rotate and a satellite rotate, but after the 7 weeks, we should be stable. Now, if we're lucky, it could take as little as 7 days, as mentioned in here. So I would say between 7 days and 7 weeks, if we've got a very high rotation, maybe 7 weeks. But my feeling is, if you look at the stats, it could be 7 days. it's just how the satellite would rotate around the Earth. Now, this is actually not accurate. Because of that permanent magnet, the satellite will actually rotate 180 degrees when it gets to the equators, not the equators, to the poles. And that would mean that the antenna would point to the outside and not inside. But from a solar panel illumination point of view from the sun, we will have the same amount of panels still looking at the sun. So we could use this principle to sort of calculate how much power we can get. If you look at a worst case scenario deployment from into space, it would probably be the International Space Station. Now, if you look at all those curves that I've got here on the right, and you try and do a calculation of sun illumination period of the total rotation around the Earth, we will roughly have a 66% illuminated path. So 66% of the time, we will have sunlight on the solar panels, and the rest of the time it will be in the dark side of the Earth. So basically what it means is we can only have 66% of the time we can charge and run off if the batteries are full, and the other percentage will be we can run off batteries if the batteries is still alive. So this is just different configurations of how the solar panels get configured. And the reason why we look at different configuration, in our configuration, we've got this whole line is a set, this is a set, this is a set, and this is a set. And this will all be linked to this connector. And we will use Schottky diodes to combine the power of these panels to be able to eliminate the capability that if one set of cells here could fail, that it doesn't affect the whole panel, but at least we could still get 3/4 of the power from the other panels. So there is some thinking behind how we could protect ourselves if we have some failures on the panels. That's very low dropout Schottky, so the efficiency loss that we'll get hopefully is not too big. Then we will probably not have a sun-synchronous launch, and therefore I've already explained the 66%, but how often will we be able to see the actual satellite on Earth during a day? So depending on exactly the launch, but we could see 1 to 2, and if we're very lucky, 3 visible, or in some cases 4 views a day. Now, looking at the altitude that the satellite will be launched, we're probably going to have only a maximum of 20 minutes. If we're that lucky, if it's a worst case scenario, then maybe 10 minutes of time we could actually use a satellite. So we have to look at how long we can basically use it. Now, if you look at the actual paths in 13 and 14 years, the ones that sort of normally works on International Space Station, so a full rotation would be 1 hour and 43 minutes roughly, or 1 hour and 51 minutes. That's sort of the time we'll have if we work on this 560 or 786 mile altitude. So that just gives you an indication of roughly how quickly it does rotate around the Earth. This is still more calculations on the actual angles and so on, just to confirm that our calculations was correct, and we recalculated based on some other theoretical angles that was given by other solar power companies. And we just wanted to verify that if we use the curves that they had and the curves that we had, we were actually pretty close, that our calculation was correct. Then there's another problem, right? So the other problem is because we will be rotating in that first 7 days or 7 weeks before stabilization, we will get these pulses or in sun, out of sun per solar panel. So depending on the angle, so certain solar panels will get a longer view while it's rotating. Some will just get short pulses, but very 90-degree angles onto them. And we have to make sure that if these pulses comes in, that we do not affect the power supplies or the processors and everything else that needs to harvest this data and charge the batteries and everything. So what it actually means, we need reasonably large capacitors to compensate some of these pulses in the actual power supply, which is quite important. And these are based on other satellites and their observation of the amount of pulses that they were getting. So you can look at this as minutes. This is sort of based on minutes, so it's 200 minutes. That's just the sort of pulses they were getting, right? So that gives you an indication, and yes, it hours per second. So the criteria of our power supply, it needs to operate from -40 to +85. We hope to be able to put it close to the battery, and between the battery and the actual RF stages, which will be the power amp stage and the SDR receiver, those units will be the warmest of all components, exposing some heat, and hopefully that will keep the temperature reasonably stable. We're going to have a 5-volt booster regulator, and I'll explain to you later on some more details how it works. We need the under and over voltage protection capability so that if something goes wrong, that we do not obviously blow up the satellite. Overcurrent trip with auto resets. So if something does go for some odd reason and it's using too much current, that the actual satellite can retry and continuously retrying, because what we've seen on historical satellites, that they do eventually sometimes recover where that component eventually failed properly and becomes open circuit, and the rest of the satellite could then operate. We've used a lot of capabilities in a sense in the power distribution, where we use rectifier diodes to eliminate certain things, and I'll explain to you later on. We've actually redundant power supply capabilities. If the one MPPT controllers would fail and so on, the other one will take over. They've got battery protection circuits, they've got overcurrent circuits, temperature compensation circuits, and I'll explain all the details later. And then the power supply needs to be not to be noisy. It doesn't need to have a lot of EMI, otherwise our satellite receiver will not receive anything, and then that's no use for us either. So because our solar cells will be operating between full illumination and almost zero, if we can harvest the whole range of power from the satellite, from almost zero till a maximum, which in our case would be about 12 volts, then that means we will get the maximum amount of power from the cells. So we will be using an MPPT controller, which could harvest the power from 3 volt to 12 volt. So it means if the one solar cell only produced 3 volts, and any of the other cells up to 12 volts, we will still be able to harvest some kind of power from the 3 volts and add it to the actual total power that we're getting from the solar cells that's fully illuminated. So we need at least 3 to 4 independent controllers, although we've got 12 solar panels as such. Maybe if we can have all 12 on their own MPPT controller, individual ones, then that will obviously be the first choice. But because of space limitations. If we have between 3 and 4, that already will be a good harvesting capability. And in fact, we've put 6 of them on the board that we've designed. The channels must be connected to a pair of solar panels. So what we're saying is, because we've got 13 panels, we can have, because we've got 6, we're going to have to double up 2 solar panels to 1 MPPT controller. And basically, the theory that we've taken is we took similar illuminated panels and put them together so that we will get similar voltages and current from them, and not have one fully illuminated and one not fully illuminated, because then we lose the one that's not fully illuminated as power capability. So by selecting the correct panels, then combination is very important as well. What else do we have? Battery charge regulator. We obviously need to regulate the battery charging capability, and we need to have over and under charge protection, with also a capability that we need to build in there is the capability to, if the battery goes short circuit, that it will eventually disconnect the battery and allow the power supply to operate normally, giving power supply to the onboard computers and the SDRs. And what that would mean is then the satellite will only operate when it's in sun, and if it's in the dark side of Earth, it will switch off. So that capability needs to be built into the power supply. That's a requirement. We also need a before flight charging capability. That means that we need to be able to plug in a USB cable into the satellite to be charged before flight. So normally what they do on the International Space Station, because the satellites might sit in the space station for 3 or 4 months before they actually get launched, then just before launch they will quickly charge them, and then they will launch them for us. So we need that capability. And obviously if the satellite, if we're flying somewhere and we need to mount it on the launch unit, then we also just want to charge everything before we put it on the unit. So, and we don't want to open the satellite to do that. We just want to plug something in the side and charge it. So the modes of operation, that's important. It's solar only operation, battery and solar operation, and battery only operation. So the battery only is for nighttime. Battery and solar is, that means if during the day it can give us enough power plus charge the batteries. And some solar only operation is when the battery has failed and we want to operate the satellite. So we've done a large research on different controllers, MPPTs. As such, we've decided on this specific unit because of its large capability for harvesting. We also wanted something to protect the battery. We wanted something to protect, if the battery goes short, it should still be able to operate and give us voltages. What makes this specific unit very powerful is its efficiency. It's got a really high efficiency. It's 92%, if I'm correct. It's got a very configurable capabilities where you can set current limits, you can set charging limits, switch on times, emergency switch off. It's a very small physical device. It's small, it's I2C controllable, so it means we can communicate with it and adjust certain levels of charging, currents, cut-offs, all kinds of configuration, which is really a powerful capability, which covered, I would say, 95% of our requirement, which I previously mentioned. So this is just some more details on the chip, which is, I think, a very important capability here is the watchdog. So this chip has got built-in watchdog capability. So even if it gets affected by solar radiation and it is put into a state where it's sort of in a reset position, then the watchdog will wake it up and it will carry on. So it's got an onboard little processor, I would imagine, that does all these things. And it's got a built-in boost buck converter, which is the capability from the solar panels to give us a continuous output power. And if you look at the sys section here, so you can define by adjusting configuration in here what output power you want. So because we're going to have 6 of these units, we're going to define them to all to have exactly the same output power, independent from what the solar panel input voltage would be. And then it also has got the charging regulation capabilities, and it's also got this capability here where it will disconnect the actual battery if it does go to short. So you can short this out, it will recognize that, and it will then disconnect the battery automatically, which is really a powerful feature, something we didn't have to build external to the device. It does it all for us. Then the battery connection, that's the battery voltage sensing. It's got a very extra leads for battery voltage sensing, which is important because of track lengths and things that could affect the measurements. Although we could override it with I2C registers in here, it's important things to think of. Temperature sensing has got a temperature sensing, so it will sense the battery charging temperatures and then reduce or increase the charging. That really normally extends the life of the batteries. So because we're going to have 6 of these ones, we're going to have to set those levels a little bit lower so that we can then not over or under compensating based on temperature. I think that's sort of at high level what's important. I think that's all I'm going to talk to here. This is just how the solar panels will be connected together. And then we also require, now we've got a sys voltage out of those regulators that comes from a battery, and we're going to need 2 boost converters. And the 2 boost converters that we're going to use is for 3.3 volt and 5 volt. Most of our circuits will be using 3.3 volt, and we're going to have a 5 volt for the RF power amp stage for the transmitter. So there will also be an onboard Atmel 16 processor on this board. And the reason for that is so that we can actually update these registers and configure the actual settings that I've just discussed remotely. It's not a train smash if this processor do get upset and do not operate at all, because these units can operate independently from the I2C. It's purely an extra capability that would help us to, maybe in the first month of operation, we can adjust some of the levels and configurations so that the actual regulators will work at the optimum level, because we are simulating the intensity of sun and view angles of what is going to be harvested from the solar panels, but subtle adjustments can then still be done from Earth after we've read the telemetry data. So that's sort of the thinking here. Then the power supply unit also needs to be able to switch off the 3.3 volt and the 5 volt power supply. And the reason for that is that its first point of operation would be to keep the batteries fully charged. And if we feel that the batteries is overused, it should automatically switch off the 3.3 and 5 volt and wait for it to reach a certain point, and then it can start switching it back on. And then we've got another switch that we will have here, which is these 3 are all FETs that will be switching on our antenna deployment component. And that is in the beginning when we open up the panels, as well as opening up the antennas. This is a quick view of the design. So we've got the boost controller, we've got the solar input, and then we've got a PC104, which is the interface between the different boards. And that's sort of how we've divided the design. Certain lines will go directly from the solar controller unit where the MPPT sits and straight to the PC104, and some components will go to the boost converter and to the PC104. So this is a bit small, but basically you can see from a design point of view, this is the solar connectors, which we actually changed. It's not like this anymore. There's the 6 solar chargers from the solar panels, and then this is the USB charger. Remember, we also need to charge from USB. This is the onboard computer. This is a USB serial interface, so we can program this unit. And this is a I2C duplexer, so we can talk to all these devices from this microcontroller. This is a local dropout regulator that just gives power to this CPU. This CPU will be in sleep mode 95% of the time. I will wake up every now and then just to see if everything is okay. The rest of the time it will not operate. There are some more details on the actual Max chip and how it's configured. I mean, you can go and read more about it. Or it's got built-in FET, so you don't need external FETs. It's only part that's quite large that you need to add externally is basically the inductor for the buck boost converter. This is the boost converters. This is the 2 converters that will generate our 3.3 volt. This is the 3.3 volt, and this is the 5 volt. These need external FETs. And so our single point of failure obviously is here. So if one of these 2 would fail, we are dead in the water. So this is really a critical part of the whole circuit, and we've over-designed this by far so that it doesn't run, or I think we've even got a 50% efficiency. It's going to run at about 50%. So I think we've over-designed it from that point of view, so that it should last for quite a long time. Okay, that's just the PC104 interface. This is where we're going to send all the control I2C data between the different boards, antenna deployments, and so on, and the power supply voltages. Just another details around it. This is the new version of the board. This is version 1.1. We designed version 1.0 where we made a mistake. Luckily, we realized our mistake and we could stop the manufacturing of the boards. We've done a version 1.1. We've sent it to the manufacturers, and they came back to us and said that we should not use blind vias because that will increase the cost of the boards. This is a 4-layer board. So the reason we try to use the blind vias is to make the components fit easier. But we didn't know that the actual cost for doing blind vias is so extreme, and we just now readjusting the vias to be through all vias to be able to bring down the cost for the PC board manufacturing. There's quite a big difference. I mean, I think we wanted 5 or 6 boards, and the difference in cost is between 16,000 and about 4,000, right? So it's a dramatic increase in cost, and they can't do blind vias in South Africa. It has to be sent overseas. So this is just an explanation of what a blind via is. We've got 4 layers. So basically what it means, in some layers, we've just brought it down 1 layer and the actual hole is not right through. So that's a blind via. You can see there's quite a few of them in here, and we are busy fixing that, and we will resend the boards to the manufacturer. Interconnect, there is something that we almost forgot. So there is a requirement from the space agencies that none of the power supplies are allowed to be connected during the flight into space, and only on deployment we are allowed to switch on all power. Now, that's something we forgot on our CPU board, onboard computer, is we had a real-time clock battery on there, and we thought that could stay on, but even apparently according to the regulators, we even have to disconnect the real-time clock. So that's something we're going to have to add onto the power supply unit to be able to disable and enable the real-time clock for the onboard computer. I think the rest is straightforward. So what is a battery, a space-grade battery? It's a battery, two types of power storages. The system that are used in satellite power systems classifies based on their electrochemistry, right? So I think if you look at the type of batteries that's available and you look at the capabilities and their capabilities over a large temperature range. So we looked at NiCad, NH2, LiFo, Lion, there's quite a few. And I think we actually eventually went back to NiCad because the new NiCads is actually very similar to the, I think we looked at the ferrite version, which was the best 3 or 4 years back, but now the has come to the party. So what do we need to do to protect our battery? We do not need to discharge it less than 50%. If we can keep it above 50% all the time, and that's what we're going to try and work towards, right? That means that the lifespan of the battery would be extended. So what that means is we might have to switch things on and off depending on the battery state, and therefore it might affect functional capabilities on the satellite, and we might put it in sort of a backup mode in certain times. What is the shelf life? I mean, these batteries, they shouldn't be longer than 2 years on the shelf. 80% of rotation around the Earth. So 80%, like I mentioned previously, 66%, we're going to hopefully have sun. We don't need to overcharge it. So our controller, this MPPT controller, we have decided here it's got 4 modes of charging, and it will, fast charge, slower charge, and then it will actually just trickle charge. I can't remember what the other mode was. Overheating, once the maximum voltage is reached, that's quite important that we don't do that. Operating temperatures, that's the battery temperatures we need to try and keep. You can see -5 is quite, our satellite might be much colder than that, so that's the reason why we want to put the battery close to the transponder and the regulators so that they do not become too cold. Resistance and shock and vibration. Obviously, we need to mount those batteries in proper housing. We're going to 3D print housings around them to sort of make sure that they do not vibrate or hit some boards and stuff around it and break off and things like that. Power usage management, obviously that's all built in the MPP3s that I've mentioned. And if it does get to extreme cases, then we will go into self-protection modes, which will only run the beacon. Weight and size is quite important. So I'll show you how we decide charge and discharge cycles. Maximum cycles, 100%, 90 minutes cycles is roughly what we're looking at. Battery charge time, 55% of 90 minutes is what we're going to require to fully charge it. Battery consumption, 100% for 90 minutes. That's what we hope to get out of it. And we've decided to use 2 18650 lithium-ion batteries, but maybe higher spec versions, military type versions, so that we can get a longer lifespan out of them. So total charge capability would be 7,000. You get higher quality, higher charge versions, but we've looked at curves to look at the amount of charge you can keep against the lifespan of them, and I think the value that we'll get is the best out of the 7,000 milliamp batteries. Sorry, the 3,500, which will give us total of 7,000. As more criteria, I'm not gonna give you more. This is just how we did the selection to get to that battery. We did a lot of calculation. We look at a lot of graphs, a lot of statistics from different universities. Here is also some graphs. How did we get? We looked at the ones that could handle the temperatures, the one that could lifespan, and so on and so on. So that's how we got to the battery. This was our generation one power supply, which had a defect. This is a total different concept. We've done here was all analog. There was no switch modes, no boosters. And the problem here was that if we were not in sunlight, the logic in here said that our onboard computer should switch on the power or switch off the power, but it would not help because it would have disconnected the power to the onboard computer. So we solved this with the new power supplies. And also we've now upped the efficiency dramatically. I think we've got 3 times the power generation. Just a view of how it's going to be distributed, a different view of what we've just discussed. Another way of looking at it. I'm not going to bore you with this. This is the onboard computer. I just quickly want to show you this. So we're going to have to build a version 2 of this. And the reason for that is we've got the watchdog timer. This is this unit here, which we left out the track to here, and it will not work. So if we add that track, then the onboard computer will, after watchdog timer, will work 100%. So, and then we've got another small problem is this RX interface connector is pretty small. It's very difficult to operate it. So we're going to increase that. And then we're going to make the small change for this 3.3 volt battery so we can disconnect it when the satellite is launched. Only then will this 3.3 volt battery needs to switch on. And that's a requirement that we have to add to the power supply. Okay, I'm going to take a break here before we carry on where we are with the complete satellite. So any questions at this stage before we carry on?
Okay, if there are any questions, please show your hand. I don't see any hands. So,
okay.
Okay, hang on. Whoa, there now all of a sudden. Burns in the US showed his hand. Burns, go.
Hi, yeah, excuse me, I was trying to understand what form of MPPT you're using. In other words, is it based only on temperature, or is it a perturb and measure kind of thing, or how do you figure out where the maximum power point is?
Yeah, if I'm correct, Vince, it does both temperature and curve, and it's got digital registers inside it where you could actually adjust some of the curve. So you could set the PowerPoint curve. I can't remember. I can maybe send you the PDF. It's quite configurable via registers where you can adjust the curve level. So if you realize that your curve is maybe operating, let's say from 4 volt to 8 volt, and it's not linear, a straight line, you can adjust certain parts of it up or down. We haven't done the software for it yet, so I need to go and actually have a look in the actual document to exactly understand how much of it you can adjust, but that's basically the plan.
Okay, thank you.
Okay, I see
Any?
no other hands.
Hello, Anton.
Any? Okay, go.
Yes.
Thanks. Just to make sure, is that a lithium-ion battery?
Yes.
Yeah. Now all the old cells packed up. You heard of the burns say that they tend to short circuit the old type cells.
Yeah, but I think we've decided right from the start that we would not go for the old type, but we would concentrate on lithium
NiCad.
ion and they even no NiCads and the lithium ion. I mean, there's a lot of new developments there too. So as Anton also said, we may well look at an upgraded battery still.
Yeah. So I think when we had the discussion with Burns, when was it, in July? I think they did a equivalent evaluation, and they also, I think, decided on a similar battery that we're going to use. So I think we're not far off when we choosing our battery.
Yeah, that's what I recall.
Yeah, correct.
Any other questions? Right, Anton, I think you can go ahead with your update. You can make that quite quick so that we can finish in about 10 or 15 minutes.
Okay. Quickly just back there. All right, can you see the presentation?
Question mark, yes?
Okay, good. Okay, so what is completed in AfriCUBE? The onboard computer is complete, but that small bug that we need to fix with the watchdog timer. The RX board is done, and that works pretty well. We've even got the software to do the Doppler drift adjustments for the control stuff. I think I've got a 40 to 50 kilohertz Doppler adjuster. So when we're going to send any control commands to the actual SDR receiver, we're going to send a small carrier up front. Before we actually send the modulation, it will lock immediately and adjust the Doppler. And so in theory, we should have a reasonably good transponder communication for control. Space frame. The space frame is done, except for the two legs where we need to put the two springs in. It's like two little springs that needs to push the satellite away from the other satellites in the P-pods that we still need to do. And then there's a micro switch that will go on the third leg to indicate the satellite is now deployed. So that little switch we also still need to drill out on the leg and put that into place. And Gary hopefully will help us with that. Battery selection, we've completed that. Permanent magnet stability board is done. Antenna is done. We might look at the smaller antenna a little bit later, but if we run out of time, we'll use what we've got. Solar panel selection is done. Most of the mode control software is done. So I'll maybe show you what we've done there. Outstanding antennas, antenna deployment board. So that's a little board where we're going to have the two resistors that will be heating up and melt the fish line, the nylon line to open up the doors and antennas. Remove before flight deployment switch that still needs to go on the same experimenter board. Space frame leg required. The spring that we've discussed. Testing of new high power transmitter board. So we're going to hopefully fly the new high power transmitter board on Bakar. Maybe not this year, but possibly next year. But I understand the Bakar flight was postponed to next month, so maybe we'll fly then if they've got still space for us. Revision 2 of the high power board with additional forward and reverse power sensing. We want to add the SWR capabilities on the actual power board so we know if the antennas are deployed properly or not. Antenna matching circuit. It's a little PC board that will sit at the top with the matching circuits. Once the antenna is deployed, we will analyze, put it on the analyzer and adjust the matching circuit so it's perfectly matched. Revision 2 OBC board, I've discussed that. Building new springs for the doors. The existing springs we have for deploying the doors is too strong. We have to use different material, and I think Henny has given us some good suggestions to use, what materials to use there. So we still need to try and find that material. Build and test a new power supply. Testing mode control from ground station. I mean, we've done some tests, but I think we need to have much more testing around that. Testing the automated mode control and protection mode. So this is the 14 modes that we can have. So we're going to need to test all those capabilities rigorously, in the sense that we need to make sure that these things work always. There shouldn't be any glitches anywhere, especially that mode 10 where we want to reload the operating system from SD card in worst case scenario. So that one would be a last resort, and I think that's something we need to test, retest, and over-test. The other modes are just to enable the different telemetry capabilities, transponder on, transponder off, and that will give us different power usage capabilities. So depending on how much battery capacity and power we have, we can combine or switch on different modes. Then it's still vibration tests, vacuum tests, and then we need to test the deployments out of the P-pods just to make sure that everything is still the right sizes. It slides out quite easy. Sometimes you miss something. That's just the micro switch stuff we still need to add on the one board for the legs. There's some new spring on the AfriCUBE satellite. The two springs are placed in the door, and it looks like it's working reasonably well. Okay, so those were the springs that you saw there. This was during manufacturing of the doors, for door panels and so on. Jacques was working hard to get this working. You can see the machine cutting stuff. This is the high power transmitter board, which we've tested, and it works reasonably well. This is what we still need to do, is the actual fish line resistor with a micro switch, which will tell us that the actual fish line is actually burned or not. So we want to do basically this configuration. We might not use a resistor, but we're actually going to use a tungsten material which can be reused probably 20 or 30 times, so we can heat it up multiple times until the fish line, if it doesn't get burned the first time for some odd reason. That's the micro switch that we're going to put on the leg, and this is the remove before flight, what we're going to put 2 micro switches in there, because this will have to handle all the power in the satellite. So if one fails, then the satellite is blown, so we're going to put 2 in to double up the capability. That's the springs that we need to still put in the legs that needs to push the 2 satellites away from each other, and you can buy it offline. That's basically when the 3 satellites gets deployed, they push each other away, and that's these little springs that we need to put in. This is the FM capabilities that we've put in, automatic frequency control for adjusting for Doppler, and that's what I discussed earlier, that this is how it was working. Basically, if you've got a carrier that's off center, it will pull it in automatically at the center point, and it works like a charm. It does it in microseconds. It pulls in that PLL really works well, and that's it.